Okay, so I've officially done. I've derived. So I proposed a problem. I was like, what if we have a box sliding down a quarter pipe? How could we get an equation for the velocity? To be fair, I did see this problem done by someone else online, but I did not see the solution. So I saw, what's going on here. It seems like an interesting problem. It's not that straightforward. So you can see in front of you, that's my derivation. I'll go through it in a minute. But I'm going to tell you about this. What is this? This is that same problem without friction. Look how simple it is. Literally just little components. Okay, first, I'll walk you through my assumptions because it's kind of the basis of this whole derivation. And the assumptions are the same on both, essentially. So for a frictionless quarter pipe, we're saying assumptions. We're saying the arc is greater. The arc is a quarter of a circle. A radius r makes sense because a quarter pipe is just quarter of a circle, and we're gonna measure theta from the top of the arc. So if you think about it, the top of the arc is theta equals 0, and then theta equals pi over 2 because you're only going quarter of the circle. And we're just saying it starts from rest. Here I just made, I just did it in terms of energy, really simple. With components, we got the components, your mg cosine theta, mg sine theta, easy shit, basic dynamics. Gain of kinetic energy, and we just equated them, solved, and there's your equation. V theta equals root 2gr 1 minus cosine theta. Easy, easy. And then we said at the bottom, it's even simpler. And that comes up later in the rest of the derivation to prove that it's the same. So, what's going on here? Same scenario, we just have that friction acting. That's the only extra component, as you can see, the only extra component, and it makes it that much more complicated. So we have the same assumptions, other than the fact that we have friction, which here, we always know friction tangential to the, opposing the direction of motion is mu, the frictional coefficient, times the normal force, normal reaction force. So what are we doing? We're first easy, just equating tangential, parallel to the direction of travel. We're equating forces. F equals mg sine theta minus the friction, because we're saying, friction equals mg sine theta. We're just saying it's in that stationary point right there. So F is what? F is ma, Newton's second law, easy. We're going to do it as a differential equation. dv by dt equals mg sine theta minus mu n. But we want t to be theta, right? Obviously, we're not looking at it in terms of t. I mean, we said it's t because it's acceleration, but we're not looking at it in terms of t. We're looking at it in terms of theta because we're not concerned about the time. We're concerned about the angle it follows through. So some basic chain rule: dv by ds, ds by dt, ds by dt is just v. Easy. It's an easy chain rule right there. And then we just have v dv ds equals v over r dv by d theta. But why is the r there? Because the arc length s satisfies ds equals r d theta. Makes sense? Come on. Basic differential equations. Come on. Then we move on. M over R, we have that V dV theta. We just subbed it back in. Simple shit. Mg sine theta minus, we have easy. This is at the end of the day a centripetal acceleration problem because it is centripetal, it's circular motion. It's just a quarter of it. So we will be taking acceleration as V squared over R because that is the equation from centripetal acceleration. I can derive it if you want, but it's pretty simple. So we sub it in, and now we're talking about components perpendicular to the direction of travel. So we're equating. Easy. We have mv squared over r equals n plus mg cosine theta. We have that easy, simple. Rearrange for n because, we kind of need it right now, and you'll see why. After that, you do that. We have n, we sub n back into this equation over here. I should be using the laser pointer. I thought it was cool. So we sub that into there. We have this and sub back into the original equation for tangential. And then we just have this little thing over here, so cute. But it is pretty problematic. It's not that cute. We have a v squared, and we have a v dv theta, d theta. And that v squared is just going to be annoying, and the v dv d theta, that whole term is just going to be not ideal because you have the square, the actual term, and you have the derivative. Like it's just problematic. There's a lot going on, and we'll take a linear approach because it's going to be much simpler. Linear ODE is going to be the meta here. So we're gonna use y. I said y theta equals v squared theta. Simple. Cheeky little differential equation over here. Just differentiated v squared, and you have an expression for this. For v dv d theta, you're making it into half dy by d theta, and you already have this y theta equals v squared theta from the assumption. Not assumption, but we're letting it equal that. Sub it back into the equation. There you go. There you go. Then cancel out m's. Pretty arbitrary, simple. Times by r. We don't want that fractional r like y. Just times by r. We have two fractional r's. Just do it logically. You don't want those there. Why would you want them there? So now we have this. Chill, right? We're chilling so far. Next part of the derivation. So we're over here. What do we notice? What do we notice, guys? Come on. Integrating factor. That's what we notice. It's in that form. We're looking at this half dy by d theta plus mu y equals this. I just rearranged it. That's it. Times everything by 2. This is why we're doing on the half, guys. Why we're doing the half. This is in form this. This is the form that we use for integrating factor in ODEs, linear ODEs. And what do we say? The form is that. So p of theta y q of theta equals q of theta. And we're saying p of theta is 2 mu, which is constant. That's apparent over here. And q theta is our function, basically, which is this. Rg sine theta plus mu cosine theta. So our integrating factor is essentially, I don't have to explain integrating factor because it's going to be a much longer video. But essentially, it's just going to be e to the power of the integral of 2 mu with respect to d theta. Because thetas are variable here. Which just differentiates to that because there's no thetas. We're chilling. Times everything by the integrating factor, as we know. And then integrate this. Differentiate this. This is the derivative of this. This is the derivative of this. We know this. This is just basic integrating factor ODEs. Look into it. After that, we have a function in terms of y theta times by the integrating factor. Take out the constants, integrate, and what do we see? We see this little cheeky integral over here, and we're saying from 0 to theta, of course. I didn't want to say pi over 2 because we're just saying 0 to theta. It's going to cancel out anyway. What are we looking at? We're looking at this cute little integral. We take out the mu as a constant. That's chill. We know for these two, their general results, you should know their general results for integrating factor times sine theta. This is our integral. This is our integral. This whole little nice little thing over here. And similar for cosine. Oh, I don't know why that's an S. My bad. So that's supposed to say theta. I will correct it right now. That's theta. Okay. So we have these standard results. Okay. These are the same. This is different. I'll derive it. I can prove it, just not now. I can now, but look, this is not what this video is about. This video is about the velocity. Okay, we're back. Sub this in, those general results. That's our integral. Evaluate it, do some manipulation. We end up with this cute little thing over here. Back to our main equation. We just did all that. We just integrated that. Sub in the result that we got times 2 RG, of course. That's what you get over there. Nice, nice. Divide by the integrating factor is what I did. Just eliminate it, you know. And I just wrote this. I wrote it as minus. It looks nicer, you know. I wouldn't want to have a random fraction going on in this big ass bracket. Uh, and we're just gonna go back to y theta equals v squared. We're back to square one. V squared theta equals this function over here. That's yeah, that's what we have. Uh, and that is the equation. That is velocity. That is the velocity for any point on that quarter pipe with friction accounted for. But why do I think this is correct? This is a complete derivation on my own. Like, what am I pulling this out of my ass? You never know. So we're gonna check it. Of course, we're gonna check it. So our checks. What are our checks? Theta equals 0. You know, this. I thought this wasn't as strong as a check as the next one. So we're gonna just talk about it briefly. At theta equals 0, brackets equals 0. So the function v theta equals 0. You know, that makes sense. Pretty arbitrary. The next one is really what, you know, sealed the deal. I was like, okay, yes, I did get this right. So at mu equals theta, so when there's absolutely no friction, because, you know, you have f equals friction equals n mu. So if this is 0, then that whole thing is 0. So there's no friction. You get the point. It should equal this, which is our original equation over here for no friction. Right? Right? That makes sense. Should evaluate to that if the theta is, if the mu is 0, because that means no friction. So that's our function. As you know, we have this little, not so little thing. And then you just sub in 0 for the mu's. That's 0, 0, 0, 0, 0. Then rearrange, move some things around, and would you look at that? Same exact thing. V theta equals root that. Same exact thing. Therefore, when the friction is 0, that's what you get. So with friction, it's this. Well, that's v squared. So, you know, you square root it. If you'd like, you can square root it. Why the fuck not? That's your little cute answer. Not so little, not so cute, but that's your answer for what the velocity is of a cube sliding down a quarter pipe with friction at any point given theta. Okay, thank you for watching my video. This is unlisted anyway. I don't think it's gonna be uploaded on YouTube. Yeah. Thank you. That's my derivation. Yusuf